Let's talk about the specific heat of gases. We already have talked about specific heat of solids. So similar to solids, we can write the formula Q is Nc times delta T. So if you give some gas, let's say N moles, and you pump in Q, there's an increase in temperature delta T, because of this Q, and all these are related. So you see Q is proportional to the number of Q is actually actually delta T is inversely proportional to N. As you can clearly see, delta T is proportional to 1 over N. Moreover, delta T is proportional to Q. The more heat you put, the more temperature you raise. The larger amount of gas you include, the lesser temperature you raise for the same Q. So this is clear. But the thing is, when you pump in Q, is the volume or the pressure of the system is going to change. I mean, the system itself is going to change because temperature is changing. So the how do we really? I mean, what is the way? I mean, we don't know how the system is going to be in future. It can have a different specific heat because the system has changed. It is, I mean, very unsimilar to solids, in which case the solid was there, you give heat, it raises temperature, give it more heat, it raises more temperature. In this case, system actually changes. The velocity of the guys inside all changes. So that's why there are two different specific heats that has been defined. First is called molar specific heat at constant pressure. By molar we mean we just talk about 1 mole, so we set N equals 1, and the same formula is written as Cp delta T. Similarly, we also have molar specific heat at constant volume, and this is written as Q equals CV delta T. So this is for 1 mole Cp. So if you have N moles, you put N in top of that. So if you if you pump in energy Q through N moles, then this is the this is the change in temperature. Similarly here. Now there is no heat capacity for constant temperature. Doesn't make sense because you are going. The idea is to change temperature, so you cannot keep temperature constant. That's why we have two different types of more specific heats. Also, if you recall from last class on kinetic theory of gases, you can, using one of the formulas, we remember that the internal energy of the system was N times half mv squared, which was same as 3 by 2 nRT. So for 1 mole we know it's going to be E internal energy is 3 by 2 RT. Now we know that if we so this is internal energy. Now if it's a constant volume process, you know, there is no work done. So Q is going to be delta E, or change in the internal energy. And we already know Q is nothing but going to change the temperature, so it's going to be CV delta T. And using these formulas, this one and this one, we can see that CV is nothing but 3 over 2 R. Now using gas constant, which is ideal gas equation, which is Q equals W plus delta E, we know that if P is constant, pressure is constant, then Q equals R delta T plus, we know delta E is 3 over 2 RT. How do we arrive this? Simply we know that W is P delta V, and from gas equation, which is PV equals RT, we know that P delta V will be R delta T because P is a constant, so we can always do that. So just using this here, and we can see that Q turns out to be 5 over 2 RT. And from here you can deduce Cp to be 5 over 2 R. There's a ratio which is defined, which is given as Cp over Cv, and this will be, as you can see, 5 over 3 for ideal gas because we used ideal gas formula. Okay, anything else? So that's about it. Let's talk. Okay, I think that's about it.